physical memory management and virtual memory management. Okay, so the midterm exam, right, so just a quick update, right? So we'll be learning about virtual memory and physical memory in the next few lectures. And the midterm exam will include everything that we have learned until this Wednesday. So next Monday, we'll have a lecture, and then the final exam, right? So next Monday's lecture content won't be in the midterm exam. Yeah, but everything that you have learned until this Wednesday will be, it's possible to be in the midterm exam. Okay, and and one more thing, which is I think there is a university policy. If you have a midterm evening exam, we will need to skip a lecture, right? So as to compensate for the time. So next Wednesday, we won't have a lecture. Right? So I think, yeah, I think when I was scheduling the time, I forgot that on Monday, because the midterm evening exam was scheduled before the semester starts. Right? So I forgot that we will have a lecture right before the midterm exam. Otherwise, we should have canceled that lecture. Yeah, but the lecture on next Wednesday will be canceled, right? And yeah, so next week we'll have a lecture on Monday and then the midterm exam. Okay. One more thing, which is I think I mentioned that the simple OS will be in exam, right? But I think this time we'll skip it for the midterm. Right? The midterm, there won't be any exam question of the simple OS, but in the final, right? I expect that it could be in the final exam. All right. That's all the announcements. Okay, let's get started. All right. So memory management in Xenu, if you have read the code of Xenu, you know that Xenu's memory management is very straightforward. Okay. So we have a bunch of blocks, and you organize these blocks in a free list. Right? That's what Xenu calls it. Okay. So in many universities, system programming course, right, equivalent to our CS 252. In many universities, system programming course, they would have a lab that asks you to build a memory allocator. Right? So usually managed by a buddy list, a buddy algorithm that is similar to the memory allocation algorithm used in modern Linux kernel. Okay. I'm not sure whether in our 252 you have built such a thing. You have? Okay, that's good. That's good, right? So if you have built such a memory management algorithm in 252, you will find Xenu's memory management very similar, very familiar to what you very similar to what you have done or to have do. It's very simple. Right? You really just organize the physical memory in a few lists. Right? So the lists are sorted by the size of the block on the list. Right? So the only difference is that now you are operating in a kernel space compared to in 2.2, you're building a memory management framework not inside the kernel. Okay. So, but the Xenu's memory management framework is simple because it's designed for educational purpose and it's also designed for embedded systems which are very straightforward. In a more complicated commercial OS, it's different. So people, almost all of these commercial OS, they rely on a virtual memory system. And it used to be that in the old days, in the OS course, we actually require students to build a virtual memory management system. Okay, it's just that nowadays it's not the case anymore. Because building a virtual memory system is very error prone. It's not easy to get it right. So in the old days, the most difficult lab in your OS course is typically this virtual memory, this lab. So but now I don't think I think we're very rarely, right? I think most universities do not have this lab anymore. I do not require you to do this memory management lab anymore. Okay. But the concept is still important, and the ideas that people studied in virtual memory management system is transferable to other contexts. Right? In cloud, you have different layers of storage management systems, and many ideas that you have people have studied in virtual memory management system is transferable to this new context. Okay. Yeah. Now let's look at why. Right. So motivation. So for me, I feel whenever you're learning something, whenever I am learning about something, the motivation is usually the most important thing. Right? Why this thing even exists? Why virtual memory even exists? Right? So let's pause here a little bit and just imagine. Right? Think about it. If you only have physical memory, and as an OS, right, you're developing an operating system that directly manages this physical memory. Right? How do you do it? Right? You organize this physical memory into maybe a list of 3 blocks, and whenever an application in a process requires, right, request some memory, you're going to pick a piece of the physical memory and allocate this memory to that specific process. That's the simplest thing that you can do as OS for memory management. Right? Organize the physical memory in as blocks, right? Memory blocks. Whenever a process requests a piece of memory, you just give it a block. That's what Xenu does. Right? In I think you are close to finish your lab 3, right? In lab 4, you will be working on some part of the memory management in Xenu, and this is exactly what Xenu does. Okay. So Xenu directly allocate physical memory to each process, right, running user application. What's the downside of this? Let's think about this. Right? So, what would be the problem of this kind of management? and that these problems that people encounter when managing physical memory directly, those problems motivate virtual memory. Okay, yeah, think about it, and if you have any idea, raise your hand. What is the downside managing physical memory directly in the style of Z?
There's limited amount, so you can eventually run out of physical memory.
Yeah. So there's a limited amount of physical memory. Yeah. So the worst case, let's say if you have one user application that requires 1 terabyte of memory, and your, for example, your physical machine only has 40 gigabytes of memory. That's actually pretty big already, right, as a personal laptop. Yeah, you'll run out of memory. Okay. Yeah, that's one possible downside. Yes.
It's not possible to like sandbox different processes. They have to be aware of each other.
Exactly, security, right? So isolation. So if you have all of the processes, they can essentially they can use physical memory address to directly see that I want to access this piece of memory that belongs to another process. Right. So imagine that your OS allocates the first gigabyte to process 1, the second gigabyte to process 2. And process 1 is malicious. It just directly tells the OS, I want to access this piece of memory that is in the 1.5 gigabytes that memory address region. Okay. So because your memory management operates directly on the physical address, there's no isolation between the processes. Okay. Yeah, that's another possible downside. Okay. Yeah, so we'll see. There are many. Oh, yes, another one. Yeah.
Wouldn't it also like run a lot of fragmentation?
Fragmentation. Yeah, exactly. Right. Fragmentation. Right. So yeah, we'll see. Right. So what does fragmentation mean? And this problem of fragmentation, right? It appears repeatedly, not just in virtual memory, but appears repeatedly in many different contexts. Okay. Right. That's a good example, right? Very good example why the concepts you learn from OS, even if you do not work in OS kernel, it's still going to be useful. Okay. So 3 problems with physical memory management that motivates virtual memory. Right. So we are using MIPS architecture as an example. So the first problem is that it is possible that there is not enough physical memory. Right. So we have a problem that requires much more. So the MIPS architecture, right, because the original MIPS architecture is 32 bits, right, which means that you have a 32-bit address space, and with 32-bit address space, at most you can access a range of 4 gigabytes of memory. Okay. So what if the computer does not have 4 gigabytes of physical memory, and the process wants to use 4 gigabytes of memory? So this problem is more obvious with today's 64-bit address space. If you have a 64-bit address space, you have much more possible memory that you can access. Okay, and yeah, you won't be able to have the amount of memory that really covers this entire address space. Okay, yeah. So this is a 32-bit program. Its address space is 4 gigabytes, right, which means that using this instruction, the 32 bits as an address, you can access 4 gigabytes of memory. But the the physical machine might only have 1 gigabyte of physical memory. Okay. Yeah. So you will only be able to use this first small portion of the address space. Okay. But it's not that hard to solve. Right? You can imagine that there are very straightforward solutions to this problem. Right? If I don't have this enough address, enough physical memory, I'll just block the remaining, right? So the remaining portion of the address space is not usable. Right? What's wrong with that? Simple, straightforward solution. Right? In the early days, people actually do that. Right? So virtual memory is a new abstraction that is developed over a long period of time. Right? So in the early days, when virtual memory does not exist, people do use ad hoc solutions, such as if you don't have sufficient memory, you just block that address space. The remaining portion of the address space is not usable. Right? People do that. After a couple of years, people realize that okay, this is really a headache, and they need to develop better solutions, and then they come up with solutions. But you can imagine, right? So in the early days, you can just directly use ad hoc solutions. If you don't have sufficient physical memory, the remaining part of your address space is just blocked. You cannot use it. Right. Yeah. It will crash if you try to access outside of the physical memory. Okay. The second issue is fragmentation. Right. I'm not sure whether you have learned about this concept of fragmentation in other courses. Right. Has other course taught about fragmentation? No? Okay. Then we'll explain this in more detail. Right. What does fragmentation mean? Okay. So here you can see that we have 3 programs. Right. Program 1 requests 1 gigabyte of memory. Program 2 requests 2 gigabytes of memory. Program 3 2 gigabytes of memory. Right? And depending on when these programs get created and started, right, you might have these memory allocations. Right? If program 1 and program 2 they get created first, then program 1 will use the first gigabytes of memory in this 4 gigabytes of physical memory. Okay, and then program 2, right? So we'll use the second, right? So 2 gigabytes of memory starting from here until here. Okay, and now at this point, right? Let's say program 1 finishes execution. Right? What happens is that after program 1 finishes its execution, we have 2 gigabytes of free memory, but program 3 cannot fit, right? Because there's no continuous memory region of 2 gigabytes that could fit program 3. Okay. So this is called fragmentation. Right? So because there will be programs requesting different sizes of memory and finish using them and releasing them back to the memory pool, they will have this, depending on the memory size requested, right? You will have these holes of memory that's left over in your physical memory address space. And the more such holes exist, it means that the harder it is for you to find a continuous address space to fit a program, right? A big program like program 3. Okay? That doesn't make sense. What would be a straightforward solution for this? People in the very early days, people do not use virtual memory. Virtual memory does not exist, but there is a straightforward solution to this. We just move the memory around, right? So we see that there are many holes in the memory. We just do some kind of cleanup, housekeeping. Right? We move these 2 gigabytes of program 2's memory to maybe the top of the physical memory address, right? And then we will have 2 gigabytes that can fit problem 3. What's the downside of that?
It's very slow.
It's slow, right? You need to copy these content of the memory around, right? Okay. So and during this copying, because copy takes I/O, during this copy operation, the other processes I/O will be blocked. Right? It will delay other processing too. Okay. But this is a very common solution, right? It's defragmentation, right? You scan the memory and find the holes that already exist, and then somehow do housekeeping, put them together to form larger continuous pieces of memory. This is a very common defragmentation or compaction techniques. And this technique, right, typically called compaction, still exists in many other contexts. But it has its downside, right? So later we'll see what is virtual memory and how does the virtual memory technique outperform the simple solution like compaction. Right, okay, that comes from. All right, the third problem is isolation. Right? How do we keep programs secure? Right? If multiple programs have the same access, right? You can these 2 programs, if both of them can view the physical memory directly, then nothing prevents them from directly reading each other's memory. So, for example, program 1 stores its bank balance at this address, right? And program 2 might overwrite it, right? So I store my video game score at the address. I already changed my bank account, okay? Right. So this is because these 2 programs, when they use the same physical address to access memory, they are getting the same physical memory content. Right. What they are using here is really the physical memory address, and so that is causing the problem. Solution. Let's think about it. I think this is an interesting exercise. What is a simple solution for this? There's typically a simple solution until people arrive at this virtual memory. It's a more complicated solution, but it solves a lot of problems. Right? It solves all of these 3 problems, and it's more elegant. Right? But before virtual memory was invented, this problem itself can be solved with some simple solution. Yes.
You could check the addresses before going to the address, whether it is in the bounds that are given to the
Whether it's in a bound, right? So essentially you're saying that the OS needs to remember which physical memory belongs to which process, right? So program 1 might register with the OS saying that this piece of memory belongs to me, program 1. And when another program 2, try to access this piece of memory, the OS should block it. I see that it belongs to program 1, you cannot access it. Right? That's a simple and straightforward solution. Right? So let the OS remember ownership of each piece of memory, and the OS also need to check on every memory access. Check whether a process is accessing within its own memory region. It's registered memory region. Okay? What's the downside of this? What's the downside of this simple solution? Yes?
There's lots of OS overhead, like having to validate every single.
Exactly. The most direct problem is that you need to check every memory access. No one is able to afford that. So you won't be able to afford that. That's going to be very, very slow. Okay. Yeah. Also, aside from that, the OS need to remember this mapping, right? So which memory region belongs to which process. Right? That's some actual overhead. But the most important overhead is that you need to check every memory access. That's going to be very expensive. Okay. All right. So that's a simple solution. Right? So now let's look at virtual memory. So virtual memory, how does this one single solution solve all the three previous problems in a more elegant way? Okay. Why do we prefer this solution? So virtual memory, its core idea is very straightforward. Right? So the name sounds daunting sometimes. Right? So what does virtual memory mean? Right? Its core idea is actually very straightforward. It's just a per program map. Right? This map is a map from program address to physical address. Okay? So what does this mean? Every program, when it tries to access a piece of memory, it does not use physical address anymore. The program themselves, they have no view, no direct access of the physical memory. Instead, each program has its own program address space. That is virtual, right? We call it virtual memory address. Okay, belong to itself. So, for example, program 1 has maybe a variable stored in its virtual address 1000, for example. Right? And program 2 also has its own variable stored at virtual memory address 1000. But virtual memory address 1000 in program 1 and program 2 are not mapped to the same physical address. They're mapped to different things by the OS. They're mapped to different physical address location by the OS. That's how the OS is able to separate the memory access from different programs. We'll look at a more concrete example. Right? So the core idea is very simple. Right? So I think at least when I was learning OS, when I was taking this virtual memory course, I got confused by a lot of these fancy terms. Okay, so and it took me a while to really understand what these things are, but their core idea is really straightforward. Right? So many of the techniques in system field are really straightforward, right? Because really complicated techniques cannot survive in system engineering, which is affected by performance overhead a lot. Okay? All right, so let's follow this idea. It's really just a per program map that maps virtual program address to physical memory address. Okay? So without virtual memory, every program has this address space, and this every piece of memory in this program address space is directly mapped to the corresponding physical memory address. For example, this address 0000 is mapped to physical address 0000. Okay, address 0001 is mapped to physical address 0001. And if you access memory, for example, 10,000 somewhere here, right? Because you do not have a physical memory, your physical memory is not that large, so that piece of memory does not have any mapping in physical memory, and you will crash. Without memory, without virtual memory, this mapping is direct. Now with virtual memory, the mapping is indirect. Right? So here you have a map. This map, the left-hand side of this map is the program virtual memory address. And the right-hand side of the map is the physical memory address. Right? So the first piece of memory in the program may be mapped to the second piece of memory in the physical address. Okay? Similarly, right, so the second piece of memory in the program may be mapped to the first piece of memory in the physical address. Okay? Is this idea clear, right? Does it make sense? It's very simple. The change is that we're adding a map. Okay? And this map is per program. Each program has its own map. Of course, these maps of each program, they are organized, they are managed by the OS. Right? These programs, they do not manage these maps. These maps are oblivious to them, right? So they are managed by the OS. But each program has such a map. Okay, so this is the core idea of virtual memory. Virtual memory is essentially just a map. How does this map solve the previous problems? Fragmentation, isolation, not enough memory, not enough physical memory. Right? So for problem one, not enough memory. So this is the map. And when we do not have enough physical memory, right? So for example, this program uses memory 0, 1, 2, 3, but the physical memory only has memory 1, 0, 2, right? That's all the data that they can fit in memory, right? So what happens to program memory 3? Oh, sorry, let me see. Sorry. I think one thing I didn't explain clearly is that so here this huge map, right, manages the memory mapping of each program, but it's simplified extremely. Right? So this is this huge map, it actually contains a set of per program maps. Okay, but this is really simplified. Right? So you see here, problem there are yeah. So I think there's some confusion here. Right? Program 0, 1, 2. Right? So this could cause confusion here. Yeah. So sorry, 1 second. Yeah. Okay. The naming here is confusing, right? So these are program 0, program 1, program 2, program 3. They are not independent programs. They are just different memory pieces used by one program. This one program. Okay. Now back to this not enough memory, this problem. We have this piece of memory that does not fit into the physical memory. Right, what do we do at this point? Yes.
You have to switch some of the programs 0 to 2 to disk to get enough space in physical memory that you can store through.
Yeah, but even before that, I think that's a demand paging or swapping, right? To enable that operation, we need to remember that this program, this piece of memory 3, it also has a entry in the mapping, but it's mapped to the disk. Okay, so here, problem 3, right? You see that memory location 0, 1, 2, they are mapped to some piece of physical memory, right, really in the memory. But this memory 3, it can be mapped to the disk. Okay, so in the future, if problem 1 is really access this piece of memory, at that time we can bring this memory 3 from this 2 physical memory and replace one of it, right? Put it back to disk. Right? For example, let's say problem 1, right? This memory 1, I put it to disk, and load memory 3 to this location. Okay. In this way, we are using the physical memory as a cache for the disk. Okay, and this is different from the previous direct memory mapping. I remember in the previous direct memory mapping, if you access this memory location 3, you crash directly because you do not have sufficient memory. But now we can see that using this map, we can remember this program location 3. It does not exist in memory, but it exists in disk. When we really need it, we will bring it into memory to replace some old entry that we might not need. Okay? Does that make sense? And so how does this map solve this problem of not enough memory? Okay. Yeah. So if we really need memory 3, we're going to put swap out, replace this memory 0, and then put memory 3 inside. Okay. So this is how virtual memory creates this illusion of unlimited memory. Right, so it's essentially saying that the memory is used as cache, and the disk is the backend storage for the memory. Okay. All right. Now a second problem, right? Memory fragmentation. How does map solve that? Okay. So because we have this map, so we can map the program's address to physical addresses in whichever way we like. Right? Remember, the fragmentation problem happens like this. We have a program that sits in the middle, and we have some holes in the physical memory. Like here 1 gigabyte, and then 1 gigabyte here. But these holes, they are not continuous. You cannot put a program in this continuous space. Right? And because we have this map, so we don't really require the physical memory to be continuous. Okay. And each program has its own mapping. So program 2's memory is mapped to the middle, but program 3's mapping can map to the top and bottom of the physical memory. Okay, so in this way, from program 3's perspective, right, think about this question. From program 3's perspective, when it's accessing memory, is it accessing continuous memory or is it accessing discontinuous memory? From program 3's perspective. When it's using memory address, for example, right, so let's assume that this is this is 1 gigabytes. Right? Let's assume that this program 3 has a function that stores around this location, and the first half of the function is stored before this 1 gigabytes, this location, and second half of the function is actually stored after this 1 gigabyte this location, right? At here, in the second half. That's possible, right? From program 3's perspective, what does it need to do? Does it need to remember, okay, in the middle, I need to jump 2 gigabytes, right? When I'm executing this function, I need to jump 2 gigabytes. I need to read its first half, and then jump 2 gigabytes to read its second half. Does program 3 need to remember that? Yes.
Program 2 doesn't need to remember that because it doesn't have any actual knowledge of the physical memory since we're using virtual memory. So from its perspective, it still needs its continuous.
Exactly, right? So here, program 3 just use the virtual memory, and the translation from virtual memory to physical memory is done by the map, right? So the program 3 will access its function normally using its memory address, right? So we will see that I will access this function around this 1 gigabytes this address, right? And I will read its first half before 1 gigabytes, and I will continue read this function continuously using my own program address. Okay, maybe the function its a program address is 1 gigabyte minus 3 and minus 2 minus 1 gigabyte and 1 gigabyte plus 1 plus 2 plus 3. Maybe that's the address range of the function. And program 3 will use this same address range to access a function. The translation is done by the map. So when the program says I want to access a memory address of 1 gigabytes minus 1, after translation will be mapped here. When the program 3 says that I want to access a memory address 1 gigabytes plus 1, it will be mapped to 3 gigabytes plus 1 here in the physical memory. Right? So program 3 does not need to do anything special. From its own perspective, it uses a piece of memory, a continuous piece of memory dedicated to itself. And the translation is done by these maps. Okay? Does it make sense? So it's becoming more and more obvious how does this one solution of a map or virtual memory solve all the three problems. Right? This is problem fragmentation, memory fragmentation. Okay. And isolation, right? Isolation is more straightforward, right? Because this each program has its own map, and this map is managed by the OS. Okay, so the OS can enforce that they are not mapped to the same memory location. Okay, right? They are not mapped to the same memory location. And so unless that the explicitly requested and is allowed by the OS and the user. Okay, so between processes, you can still share memory, but that has to be explicitly requested and allowed. Okay. Otherwise, if not explicitly requested and allowed, otherwise this memory, they will be mapped, even if they are accessing the same virtual memory address, it will be mapped to different physical memory address. Okay, in this case, problem 1 access address 1024. Problem 2 also access address 1024, but they are mapped to different locations in the physical memory by their maps. And these maps, they are managed by the OS, remember, right? Again, the programs cannot directly manipulate these maps. They are managed by the OS. Okay? So in this way, the programs cannot access each other's address space directly. Okay? All right, so what have you learned? Just a quick summary. The 3 problems with physical memory or direct management of physical memory. Right? Not enough memory, fragmentation, and isolation. Okay, these are 3 problems that motivated that we need to have this additional indirection. Okay, and this additional indirection is virtual memory, right? So it is a per program map that maps program virtual address to physical address. Okay. One thing, right? One remaining problem is that now we have this additional indirection. It means that every time the program wants to access a piece of memory, it cannot directly use that piece of memory. It needs to do this translation, right? Map from virtual address to physical address. This is going to be overhead. Okay, this is going to be a lot of overhead. And what is the solution? I think some of you might, if you have learned computer organization and computer architecture, right? Some of you might have taken it. You might know what is the solution. This is interesting. I think this is an interesting question. Might help you think about the future design of software and hardware. So we have this additional indirection. It has so many good properties, right? It solves fragmentation, it provides isolation, right? And it solves this not enough memory, this problem, right? It gives you the illusion of infinite memory, has a lot of good properties. But it's going to be very slow, right? If every memory access, you need to do this mapping, it's going to be very, very slow. What is the solution to this? Yes? Sorry? Caching. That's good. But there's a cache called TLB, Translation Look Ahead Buffer. And even forget about what it is, right? Don't forget about the cache. The core idea is that, okay, this map is so performance critical, right? We want to be able to do this map very, very quickly. And the performance overhead needs to be reduced to a very small number. So what do we do? An additional hardware.
Yeah, is there an additional piece of hardware called the memory management unit?
Memory management unit, right? Inside it, it's essentially this hardware is called TLB, Translation Lookup Ahead Buffer. Okay. Yeah. So hardware. Right? So the performance bottleneck, this map, is implemented directly using a hardware, a piece of hardware. Okay. So because it's implement it using hardware, it can be done extremely fast. Okay, so that's how this problem is addressed. But now think about the lesson. Right? Think about the lesson. It's hardware and code and software. How do they evolve together? You will see this happen repeatedly in the history of computer science. Right? So without this map, there are so many problems that each of them can only be solved in a very ad hoc manner. Right? If you don't have sufficient memory, you just hard cap the memory that you can use. Right? That's a solution, but that's very ad hoc. Right? You have a fragmentation, then once in a while you just clean up the memory, do some housekeeping. Right? That's a solution. That's very slow. Okay, and isolation. Right? So let the OS remember this the memory region of accessible by each program. Also ad hoc. Now with virtual memory, with this map, you provide a much better solution. Elegant solution that solves all the previous problems, but at a cost of a lot of performance overhead. Okay, so you have a software abstraction that has a very good properties, but it's just very slow. Now what do? We implement a special hardware that speeds it up. Right? If it's worth it, and history has shown that it's really worth it. Right? If it's worth it, we implement a special piece of hardware, right, that speed up this process, extremely speed it up. Okay. What's the argument? Why this is difficult? Think about this. In a computer system, you can argue like this. I can speed up anything in the computer system using hardware. Every part of the hardware, every part of your software system, you can say that I can speed it up using a dedicated, specially designed hardware. What is the challenge in system research, right? Or in the future, if you're going to work in build real world software and work in a company, build real world software and hardware. What is the real challenge? What can we learn from this? Anyone want to take a guess, right? I think these questions are some of the interesting discussions, right? So aside from the knowledge, right? Because a lot of this knowledge that you learn, you need to figure out how they can transfer to the new context that you're going to work on, right? So because very few students will work in OS kernel, right, in the future, right? Because it's a relatively small field, right? But the knowledge will be transferable to other fields, and this is going to be one of the important lessons, I would say, right? So think about this. You can argue that for any what is a difficult decision here? Every component in your software. Right? So if let's say I want to improve the performance of my software, right? I want to have a very low latency, high throughput system. Okay. Right, so why don't I just implement dedicated hardware for each piece of each component in my software? It also is straightforward. Right? Building a dedicated hardware is extremely expensive. You cannot afford to do that. Okay? You cannot afford to. So this TLB, these chips, do you know how much money it takes to build such a hardware from design, right? From initial design to really make them into chips? How much money it takes? Billions of dollars. Right? Billions of dollars to make a chip, right? A specialized chip for new technology. Okay? So no one simply say that, okay, my software is slow, so let's just make this piece of my software, let's build a hardware for it and speed it up. No one can do that. Okay? So now the question becomes, how do you identify the critical portion in your software or in the entire software stack where you build a new hardware, it's so critical, right? You spend some money, you spend billions of dollars to build this hardware for it, but it's so beneficial, right? It benefits the entire software stack, and your return is more than billions of dollars. How do we identify such critical points? Okay, right, does it make sense? Right, so this is one good example. Right, so the virtual memory is a good example. How you do this? This solution is essential to all problems, right? Any computer, all problems. If you optimize it, it benefits any problem that runs on any computer. And it benefits it dramatically. Okay? So it's worthwhile to really invest a lot of money and human effort to design a specialized hardware to speed it up and use this solution. Okay? Hopefully that makes sense, right? So in the future, when you, if let's say you are going to work in a big company for their software systems, you will see that in the core teams, you will reach this boundary where you need to think about whether we need to change the hardware or whether we want to use existing hardware to make some smarter design in software, right? So, or whether we really need to change the hardware. And what is the most recent example, right? Can you think about the most recent example when you need to invent new hardware?
Yeah, like specialized chips for AI, like
Yeah.
tensor processing units.
AI chips, right? TensorFlow, AI chips. Right? And right, I think maybe 10 years before AI chips, there was this specialized ASIC chips that are designed for cryptocurrency. Right? So when people see the huge benefit of implementing a new hardware that can optimize the entire software stack, that's when people build new hardware. Okay. All right. So, and this virtual memory, I think the lesson that you can take away from this is that it's a good example, right? If in the future you need to reason about what is a good software design and whether you require some better hardware, right? Some hardware to support it. So this is virtual memory is a very good example of such reasoning. This hardware is called the translation look ahead buffer. Right? So it's essentially the map. It's a cache for the map. The per program map that we have mentioned, right? So it is called page table. Right? Every program has this thing called page table. It's essentially that map. And in modern hardware, you have this translation look ahead buffer. It's essentially a cache for this page table. It does not store the entire content of page table, but it's a cache. Right? It speeds up the access and translation of these page table maps. All right, so that is the introduction. So that introduction, I think, is it's a high-level introduction to what virtual memory is, why it's designed, right, the motivation, and why I think it's important for you. Right? But now let's look at the details. Right? So the details of the implementation for these virtual memory system. Okay. All right. So usually this virtual memory management, the modern virtual memory management system is uses paging. So in the early days, although there exists such a virtual memory, but they do not necessarily always use paging. All the modern systems, they use this thing called paging. I will explain what paging is. Okay, so physical address space of program can be discontinuous, right, non-continuous, and we to avoid fragmentation and avoid the problem very sized memory chunks, we designed this thing called paging. Okay, so it divides physical memory into fixed sized blocks or called frames. You have physical memory frames, and this frame size is a power of 2, right, between 512 bytes and 60 megabytes. And nowadays there are even larger size page. Right? So in cloud systems, you have a much larger size pages. Right? 64 megabytes pages, and that also happens. Okay, and when you divide virtual memory into blocks of the same size, this technique is called page. Every block is called one page. Okay, and your OS will keep track of all the free frames, and to run a program of size n, you need to find n free frames and load the program. Okay, and you set up a page table to translate virtual to physical addresses, and backing store the physical memory and the disk can be likewise split into pages. Okay, it can still have internal fragmentation, so it only solves the external fragmentation. All right, but this paging, you will see that why learning Xinu is a good option. Xinu is very simple, straightforward, but its implementation mimics the core concept in modern OS. Right, the blocks inside Xinu, they're very similar to pages. Okay. All right. So now, address translation. We have mentioned that this virtual memory management system translates a virtual memory, a program virtual memory address to a physical address. Okay. And how the address translation is done? You have an address generated by the CPU, and this is the program virtual address, and it's divided into two components. One is a page number, and the other is page offset. Okay, so the page number is used as the index into the page table, which contains the base address of each page in physical memory. It's an index of each page that you want to access. Okay. Page offset, right, combined with base address to define the physical memory address that is sent to the memory unit. Right. Inside this page, what is the offset that you want to access? Right. That is a page offset. Page number is the index of which page. It tells you which page that the program wants to access, and index says that inside this page, which is the piece of memory that you want to access. Okay. All right. Now, let's look at the translation process. I think this, once we understand this, it should wrap up this lecture. Right? So, this diagram. Okay, I will pause here. I hope that everyone take a look at this diagram and try to think about what it means. Right, so this is the entire process of memory address translation. It is equivalent to the mapping. Right? The mapping that we explained before. It's just more complete. Right? So this is the page table, right? And essentially the mapping, right? And how I want everyone to look at this to guess how it is done and try to explain it. Right? Try to explain it yourself. If you can explain it, then you know it, and that's the entire purpose of this lecture. Right? So to learn how memory translation is done. Okay, anyone want to give it a try? I try to explain how this translation is done. What this means. So step by step. But if you can explain this, yes.
So P is the index of the page table, and at that location is yours F, which is the frame address. And then to get the physical address, it just takes the offsets from verbal address and adds it to F, and that takes you to the physical address.
Exactly. Very straightforward. Right? That's very good. This page table is a map. What is the left? So this map is a key value pair, right? Which is a key? Which is a value? P is a key. F is a value. Right? F. What is F? F is the index of the physical frame in the physical memory. Right? Frame F is the index of the physical memory address, physical page. P is the page number, right? Virtual page number that the program is trying to access. So this page table is essentially a mapping, right? Map from a page number to physical frame number in a physical address. Right? It's not written as a map, but it's a map. Right? So P to F, that's a map. Okay. And in all of the OS diagrams, you don't see, right? So I think the easiest, the most intuitive understanding is to show the map. It's really just a map. The key is P, the value is F. Okay? That's the map. And D, what is D? D is the index inside the page frame that you're trying to access. And this program is trying to access index D inside its page P. Okay? The index is not changed. Okay? So the index is not changed. So you only map the page number to frame number, and you will use the same index. Okay? You will use the same index. So that's why the D is preserved across the address translation. Okay. All right. Yeah. So the only thing that's mapped is the page number for frame number. Okay. All right. So now let's let's wrap up this with a quick discussion of the of a trade-off here. So this index D is not mapped, right? It's preserved across its translation. Okay. Remember, in the previous slide, we mentioned that the external fragmentation is resolved, but internal fragmentation is not resolved. What is internal fragmentation? It means that inside the page frame, there's still possible. It's still possible there's fragmentation. You can think about, okay, this frame F, this entire frame F, because the mapping is at frame level, so this entire frame F belongs to one process, right? The mapping is at frame level, so each frame belongs to one process. Okay? So when a program in this process, it might use this page dynamically. So it might say that I request the first part of this frame, maybe 4 bytes at the beginning, okay? And then after a while I request another 16 bytes in the middle, and so on. It might use this physical page frame little by little. And then after it uses one portion of the physical memory inside this frame, it might release it. And that's what you guys do, what everyone does, so we call malloc and free. Right? So malloc and free, very often we don't allocate a very huge amount of memory. Right? So we might just allocate a small piece of memory that's just creating one object that's very small. Right? And later we'll release it. Okay? So it's very rare. This page is huge. It's very rare that one object you allocate takes the entire page. And you could allocate a small object and release it later, and gradually you will have similar problem. You'll have similar holes inside the memory, inside one frame. Right? So that's the problem of internal fragmentation. Inside one page, fragmentation still exists. Okay? But now the trade-off, right? Think about trade-off. If you have like in between this P and D, the index and the page number, right? If you make each page frame, right, the size of frame smaller. Right? If you have a smaller size of the frame, you have less internal fragmentation. Okay, but you will have a larger number of pages. Right? You have a larger number of frames and pages. Does it make sense? Okay. You could have a smaller size of frames, but you will have more frames. With more frames, you will have a larger page table. When you have larger page table, you need more memory to store this page table for every process, and also your cache. Remember that the TLB is used to speed up this translation. How it speeds it up? TLB is a cache. It stores a part of this page table also, that from every process. Okay, we have a larger page table. The cache, because cache is unless you increase the cache too. But otherwise, if you have a large number of data and the cache stays small, then the effectiveness of the cache is damaged. Okay? So these are all the trade-offs that you need to consider. Right? So that's why, although you can think about, okay, if we make the frame size very small, then we can avoid fragmentation. Right? But you cannot do that, right? Because if the frame size becomes smaller, you have a larger page table, and you have a larger per process memory, and when the TLB size is very small, you drop the effectiveness of the TLB cache and every access becomes much longer. Right, so yeah, you need to consider these trade-offs of your designing the system. Okay, that's it for today. And if you have answer questions, come up with that.